Okay, so last but not least, chapter 12. So I'm doing either Gen Chem or biology next. I haven't made up my mind. But let's go ahead and finish chapter 12. So we're gonna go over thermodynamics really quickly. This is a very short, just things that you need to know. Delta G is your Gibbs free energy. When your delta G is negative, it means it's spontaneous, and spontaneous means favorable. Delta H is enthalpy, and then delta S is entropy. We know entropy equals disorder, and then enthalpy is the amount of energy held in a bond. So you need to know your physiological conditions. So your body temperature is approximately 37 degrees Celsius, which is about 310 Kelvin. And then use delta G naught. So delta G naught is what we call delta G at standard state, and to include pH of 7. Okay. And actually, it's low key like 7.6, but whatever. Let's say 7. Okay, makes sense. I mean, we're just setting a foundation. Make sure you know that. So, next, let's go over the role of ATP. So, it's a mid level energy carrier, meaning it's not too high and it's not too low. It's created via substrate level or oxidative level phosphorylation. ATP hydrolysis and coupling. ATP hydrolysis is highly exergonic, meaning it drives endergonic reactions via coupling. And what I mean by that is what we say is if you have a positive, let's say you have a positive delta G plus a negative delta G, reaction coupling will make the overall delta G negative because this negative number is going to be bigger than this positive number, making the reaction favorable. And that's what I mean when I say reaction via coupling. So next, ATP can donate phosphor groups to activate molecules. Okay, again, like we see in the first step of glycolysis, we can add a phosphate group to glucose, and that's how we get started with glycolysis. Okay, awesome. So last but not least for this video, we're gonna go over chapter 12.3, which is biological oxidation and reduction. So half reactions, right? This is more of a gen chemy thing, but remember redox reactions happen in pairs, right? So we have a oxidation and a reduction, okay? Electron carriers are reduced and oxidized to transfer energy. And I was about to bring it up. And our electron carriers being NADH, FADH, NADH2, and then ubiquitin QQ, etc., etc. Okay? So these are used to transfer energy. We see it in the electron transport chain, in the T-phase cycle, and so on and so on. And then anytime you see these, right? These are always going to be with oxidoreductase enzymes, okay? So you're always either going to go, and again, remember, Leo lose electrons oxidized, Ger gain electrons reduced. So here, if we go NAD plus to NADH, it gained an electron, so it's reduced. What if you go from NADH to NAD plus, it lost electrons, so it's oxidized. And same thing here, right? FAD to FADH2 reduction, and then FADH2 to FAD oxidation. Okay, and then some other electron carriers are going to be ubiquitin, which is also, you guys have probably heard it more as CoQ. And then we know we have the cytochrome C, and cytochrome B, and cytochrome A in your electron transport chain. Okay, awesome. So not to keep this video going on forever, we're just going to stop there for now, and I will see you in the next one.